Welcome to our discussion on systems of linear equations in three variables. As always, fast forward to the section you want to study, looking for this slide. Let's start off with some definitions. In order for these things to work, they need to be linear equations. They don't have to be linear, but for our situations, the examples we're going to go through, they're all linear equations with various variables. They wouldn't have to be x, y, z. They could be x with subscripts, right? And then each of those variables needs to have real number coefficients. They just can't be imaginary numbers. So we talk about a system of linear equations, or a linear system, right? In three variables is a collection of two or more equations with the same variables. And you might be thinking, wait a minute, how can I solve for three variables if I only have two equations? Well, technically you can't, as far as you can't get a single solution, right? You can't say the solution is 2, 3, 5. You're going to get infinitely many solutions or sometimes no solutions, because we all know that in order to solve for three variables, we need three or more equations in order to get one solution. Just like if we need to solve for four variables, we would need four or more equations. But in order for something to classify as a system, it just needs two or more equations. That's just the definition. We also talk about an ordered pair when we were solving a 2 by 2, right? Two equations with two unknowns. Now we have an ordered triple for a 3 by 3. And of course, if we go to a 4 by 4, we get an ordered quadruple or an ordered 4, right? Just like before, we can verify if something is a solution or not by just plugging it in and making sure it works. So if we want to verify that the ordered triple 2, minus 1, and 3 is a solution of this system, we just plug in 2 for all of the x's, -1 for all the y's, and 3 for all of the z's, and verify that it works in all three equations, which we have here. They all work. Great. This is a solution. Just like before, it is a solution. There might be infinitely many solutions. Okay, the operations that produce equivalent systems just means the things that we are allowed to do to these equations that doesn't mess things up. Because the whole idea is we want to change things around. We want things to look differently, but we want them to still represent the exact same equations. So we don't want to do anything that is going to basically mess up the equations, mess up that underlying equalities. So these are the only things we're allowed to do. We can interchange the position of any two equations. So we can take the first equation and the third equation and swap places with it. And you kind of go, well, no, duh, it's still the same set of three equations. They're just in a different order. So that's not going to change anything. Of course not. Okay, we can multiply any equation by a non-zero constant. And again, you should be thinking, oh, that's kind of a no duh, because if we have some stuff equals something, if we multiply through by 2, then it's all still equivalent, right? Still the same equation. We can also add a non-zero multiple of one equation to another. That's the one that takes a little bit more understanding. It's not such a no-duh idea. And the idea is that you can take one equation, add it or a multiple of it to another equation, create a whole new equation, and that becomes one of your new, of the 3 or 4, depending on how big your system was. These are all of the same steps that we are allowed to do when we're working with matrices. You'll notice that once we start going through this, that adding multiples of one equation to another enables us to eliminate a variable. And this is called the Gaussian elimination method, which parallels nicely with the elimination method that you would have learned in my other video where we talked about systems of two equations with two unknowns. And this is one of the reasons why I told you the elimination method was the better of the two methods to learn, because it's really the only method that works well with a 3 by 3 and above. And it's also the one that parallels with matrices. Okay, let's look at an example. So we're going to solve this system by converting it into what's called triangular form. And triangular form just means, if you think of kind of a triangle going this way, we want the first equation to have x, y, z, and a constant, and we want the coefficient of x to be 1. Then we want the second equation to have no x's, start with just a coefficient of 1 on the y, and then whatever the z and the constant is. And then the last equation, we want to eliminate both the x and the y and have just 1z equals something. And once we have z equals something, we plug it in here, we can solve for the y, then we can take those two, plug them in here, and solve for the x piece, right? So the first thing we want to do is get that first equation to have a 1x, so the easiest thing is to just swap these two. So we put equation 3 up here and equation 1 down there, and now we've already got this kind of triangular form going. Now we use this equation to eliminate this x, and if there was one down here, this x as well. So what we're going to want to do is multiply this top equation by -2, because remember, we always want to add, we don't want to subtract, because subtracting is where we make mistakes. Multiply the top by -2, add it to this one, and those x's will go away, which is what we're doing here. Take the top one by -2, add it to this one, the x's go away. This is the new resulting equation. We call it equation 4, and that's going to take the place of equation 2. We're going to pop it in this spot because we want to get rid of this x. Now, the technical steps for the Gaussian elimination method is that you always want to then make this a coefficient of 1. That's really not necessary. As long as you get rid of the x's, that's all that matters. And then the last one, you want to get rid of the y's, right? So you don't have to worry about making this a 1. And the reason why I say that is because look what happens. In order to make this a 1, we have to multiply through by a fraction, which first of all is something that we hate to do. It's a negative fraction, which is even worse. We're multiplying negatives by negatives, which means there's all sorts of places where we can screw this up and make mistakes. And we get into this nice little pretty reduced thing, right? We multiplied through by -1/3, and yay, that looks great. But now we need to get rid of this y in this last equation. And in order to do that, we need to multiply this equation by -3 and add it to this equation. Well, it was already a -3 to begin with, so now we're just undoing what we just did. It's not necessary. You don't need to have coefficients of 1. We didn't even need it up here. The only reason why we make it a coefficient of 1 is that it makes it really easy to get rid of these other things, because then we just multiply by the opposite of whatever the coefficient is. So in this case, -3, and in the previous case, -2. But just know that you don't have to leave it in this form, especially if it, like if this was a 5 and now all of a sudden we introduced a fraction. No, no, no. That's just going to make your life miserable. Leave it as a -3. And then if this was a 4, again, then just multiply the top by 4 and the bottom by 3 to get 12 and -12, right? Go back to that same technique that we used with the elimination method for 2 by 2s, where we just want the coefficients to match with opposite signs, right? We just want them to be opposite numbers. It's much better to do that than to always make it a 1 and possibly introduce fraction, because now you got to multiply and add fractions, and that's just a place where we're going to make mistakes. Okay, but if we follow the true letter of the law here with this method, we do the multiplying by -3, then we add it, which gives us this equation, and then we reduce it, which gives us this equation. And if we put everything back into triangular form, this is what our triangle would look like, right? X blah, 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 Y blah, 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 Z blah, blah, blah. You see how it's a triangle because these are all gone, and these are all coefficients of 1. They don't need to be. This last one doesn't even need to be, technically. I mean, you do eventually need to figure out what Z is, because now we back substitute. Now that we know what Z is, we put it in here, solve for Y. So you can think of that if this was a 3, when you plug in for Z, all you got to do is move this number over, divide by 3, and now you know what Y is. Take those, plug them both in here. Again, if there was a number here, you'd move the numbers over, divide by whatever that number was, and solve for X. So it's not necessary to have your coefficients all be 1s, but if it is, it just saves you an extra step at the end. No big deal. So here's the back substitution, right? We substitute the z in, solve for the y, substitute the z and the y in, solve for the x, finally have our ordered triple, right, for all three. We verify it by plugging into the original equations. You should always plug them back into the original equations, because if you made some math mistakes along the way and you plug it in beyond where you made that math mistake, you're not going to catch it. But if you plug it back into the very beginning and it doesn't work, then that tells you, uh-oh, I made a mistake somewhere. Okay, so always plug them back into the original equations to check and catch any mistakes you might have had from the very beginning. Okay, Just like before, we have both consistent and inconsistent systems. Remember, consistent meant that we had solution or solutions, and inconsistent meant no solutions. We can identify when we're going to get inconsistent systems if any time during the Gaussian elimination method, right, anytime we're doing our steps, if we come across the situation where all of our variables cancel out and we're left with just a equals 0, where a is not 0, right? So we do the elimination method and all of a sudden we get 5 equals 7 or 2 equals -3. The true definition is then you would take the number on the left and move it over and have 0 equals something that wasn't 0, right? But you don't have to take that last step. It's pretty obvious when you have 2 equals 5. That's false, right? So anytime you eliminate all your variables and you have a constant equal a different constant, that tells you it's false. And since everything we did was equivalent to the original equations, that means the original system of equations has a false statement in there and therefore inconsistent, no solutions, right? So here's an example. We start with these, we do some work, right? We eliminate the x, great, we're down to here. Okay, so now we're going to try and we want to eliminate the y's next, right? Or we eliminate the x again, right? So now we're going to eliminate some y's, right? We keep moving, multiply by 1/3 to get this. All right, now we're going to finally eliminate those y's. We add them together, but the z's go away as well, and we get 0 equals 6. You go, well, that's not true. And because that's untrue, everything is untrue. So the original system in triangular form would look like this, which is false, but you don't even know, who cares? Don't bother with this. Just basically means it's untrue. It's impossible. No solution. That's what this means, the null set. Right? So inconsistent, no solutions. Okay, what about dependent? Remember before we had inconsistent and consistent, but with consistent we either had one solution or we had infinitely many solutions, and infinitely many solutions happened when we had dependent equations, meaning two equations that were basically the same straight line. Well, that can also happen with 3x3s and 4x4s where you can get infinitely many solutions. It's just no longer the same line, it's different situations. But what happens now, instead of getting 0 equals something that isn't 0, you end up getting 0 equals 0. Everything zeroes out, and you basically just get an equation of all zeros. And then you have dependence. What happens basically is one of your equations ends up going away because it's just one of the other equations in a different form. So really your system of equations has one fewer equations. And if you have 3 unknowns but only 2 equations, you're going to either have no solution because the two things are parallel and don't touch, or infinitely many. And that's what happens with the dependent. It cancels out, you get 0 equals 0, and it becomes dependent, infinitely many solutions. So here's an example. Again, we got rid of the x's first. Then using the y's, right, we multiply by, we have our new setup. We can already see that the bottom two are the exact same equation. But if you did the math and finished it off, you would get 0 equals 0, and therefore you have infinitely many solutions. Put it in triangular form. The only reason why you want to continue on here and put it in triangular form is when you have infinitely many solutions, they will oftentimes want you to actually list what your solutions are. And since your solutions aren't going to be numbers, you have to list them in terms of the variables. So by putting it in a triangular form, it allows you to now solve, right, and back substitute and figure out what everything is. So now, because we have 0 equals 0, that can basically be interpreted as all values of z work, right? Because 0z equals 0 means z could be anything. So we now have to go back to our other equations and solve for them in terms of z. So we go back to x equals y minus z plus 7, but we already have that y equals 3z minus 2. Where did that come from? Do you see it? Well, it comes from equation 4. All right, so we go back here to our triangular matrix, and we've got this, so we're going to back substitute like normal. So we go into this one, we solve for y, we move this one over, we divide by 5, and that's where we get 3z, right, minus 2. 3z minus 2. That's y. Now we can take that, plug it back in for the y, and solve for x. Well, where did this come from? This x equals blah, blah, blah. Well, that just came from here, right? They moved the y and the z over, so you have x equals. So when you can plug it back in, you can simply solve for x. Okay, so z just equals z. Y, we solved for it in terms of z and got 3z minus 2. And then x, by doing substitution, we also got it in terms of z's. We got 2z plus 5. So this is the solution. It's actually a solution because we could also do everything in terms of y or everything in terms of z, or I'm sorry, x. You could do it all in terms of whatever variable you want. But since you end up doing the triangular form and you get z, as anything, it's easiest just to back substitute that way. And then you normally list them in terms of z's. Okay, infinitely many solutions, so there's that version. Okay, what about non-square systems? Non-square systems just means that the number of equations is not the same as the number of variables. Here's a non-square, right? 3 variables, 2 equations. Instead of 3 by 3, 3 by 2. So the same thing, we still want to eliminate the x's, add them together, we get this. Right, so now we've got our first equation and our second equation. And since there is no third equation, we can't repeat the steps and we're pretty much done. So what we do is we just move this over, solve y in terms of z, right? And then take that, substitute it back in to solve for x. Here it is here. Get this one. And then now we get that that same kind of situation where we have x, y, and z. So it has infinite many solutions, and here's one of them. This one, this one, and this one. How about interpreting linear systems in 3 variables geometrically? Well, we did it before with straight lines, and that was pretty easy. But now we have to do it with planes, right? Because an equation of 3 variables defines a plane, a flat surface. So here's what happens when you have one solution. You get these 3 planes that intersect at one point. Can you see how the purple and yellow would intersect in a straight line? And then you slice it with this other plane, and the only thing they have in common is that one point. So there's where you get one solution. That's what it would look like geometrically for all of the ones that have one single point as a solution. And that's the ultimate goal we're hoping for this. Here's what happens when you get a straight line solution. You get these planes that all kind of look like spokes coming out of the middle of a wheel, and you can see they all cross at a straight line. Infinitely many solutions. We could also get all 3 planes to basically coincide with each other. So this is just all 3 of them laid on top of each other, and then again, infinitely many solutions. You could get 3 parallel planes, just like parallel lines, and you get no solution. You could also get 2 parallel planes, the brown one and the yellow one, cut by the green one. So you get a straight line here and a straight line here, but you don't have any points that all 3 planes have in common. So that's another version of no solutions. And then you could have something like this where none of them are parallel, but you can see how they all cross and just get a line, right? So the kind of brownish and bluish one have a line here, and then the green and blue have a line there, and then this brown or orange color and green have a line here. But there aren't any points that all 3 planes share. So again, that's another version of no solution. Okay? Last but not least, we'll look at an example of an application problem. So taking a CAT scan, set up this way, so you've got beams coming in at different angles that are hitting these 3 tissue quadrants, A, B, and C. And we want to figure out, what's happening in each of those spaces. So we can see that beam 1 is weakened by a 0.8 unit as it passes through A and B, right? Because it passes through A and B. And then beam 2 is weakened by 0.55 as it passes through A and C, right? Because it's at this angle. And then 3 is weakened by 0.65 as it goes through B and C, B and C. And the idea is we can use these values. We know these results we get come from different things. Healthy tissue gives us values of this, tumorous tissues here, bone here, and metal this up to infinity, depending on the thickness and the type of metal. So now we can set up a system of equations based on these weakness readings that we got, the 0.8, the 0.55, and the 0.65. Now this is something that I hate that most books do, is they force all of these systems equations to always be X, Y, and Z. Because now all of a sudden you have to go, okay, wait a minute. Grid cell A weakens the beam by X units, and grid cell B weakens it by Y units. Why not just call that A and B units? And this would be A plus B, right? Because we know beam 1 goes through A and B. And then beam 2 goes through A and C. So here's A and C, because C is now going to be called Z. It's just stupid, and it makes me mad that they do this, but I'm going to do it this way because this is the way your books are always going to do it, and I want you to see it the way they do it in terms of X, Y, and Z. But really, anybody with half a brain knows that you could very easily just do this as A, B, A, C, and B, C, and then it makes more sense with the picture, and it's much easier to wrap your brain around, and then you're solving for A, B, and C instead of X, Y, and Z. All right, I digress. All right, so let's go back and do the elimination method, right? We want to get rid of this x. We already have an equation set up with an x for number 1, so that's good to go. We just need to get rid of this x, so we multiply this top one by -1, add it to this one to get rid of that x. That's what we're doing here. And then we get this new equation. So now here's the original one that we had. Here's the new one for the second one. Here's the third one. Now, if we were doing the true definition, we would swap these two because this one has a coefficient of 1, and then we would add them together to eliminate for the third one. But you'll see that that's not what the book does. It just says, all right, we're almost there. Let's just add them together, right? Because if we add these two together, this goes away, we get 2z. And then there's my 2z. They didn't even bother changing this to a positive 1 because remember I told you that wasn't necessary. They did, however, take this, multiply by a half because they wanted to solve for z. That is the one that you always have to do. Solve for z completely. Take that, put it back in here, solve for y. Take those two values. Well, actually, we only have to take y because there is no z value here. Take this y value, plug it in here, solve for x. That's what we did here. And now we have these three values. X, which remember was a, is this value. Y was this value, which was B, and C was this value. And if you go back to the tables, you'll see that that means that cell A had some tumorous tissue, B had some bone, and Z had healthy tissue based on these numbers. Okay? And again, I would just do it with A, B's, and C's because who says it has to be X, Y, and Z? All right, so that's a 3x3. This Gaussian elimination method works for 4x4s and 5x5s. You know, the same ideas. You just get it into that triangular form as big as it is until you get down to your last variable and then back substitute all the way back up. When we move on to matrices, you'll see that we first get it into what's called upper triangular form, which matches exactly what we've done here. And then we reduce it further, get some more zeros in there, and then we end up knowing what all of our variables are. Okay, so there's a nice correlation between the elimination method and matrices.